Hello. So welcome to today's lecture. As always, I'm going to start with a review of what we were talking about last time. And so we had been discussing how changing temperatures affects various macroscopic properties of materials. And then we were going to use that to define a temperature scale. So we wanted to assign a number to temperature. And so we talked about, well, there are various ways to do that because you could just choose some material, choose some particular property. You could, for example, very carefully measure the height of this brick. And then as the brick expands, when it gets warmer, you would see a change in the height. And you could use that number to define a temperature scale. That's not a very good choice because it's quite hard to detect those tiny changes in the brick's length. You could also use mercury in a thermometer. That's something that people commonly use. And the reason why it's easier is that you have a pool of mercury and then a very narrow tube where some of the mercury goes. And as the volume changes just a little bit, then the mercury will go up and down in the tube a significant amount. And then last time we talked about, is there some simplest choice that we could make to define a particularly nice temperature scale? And I said that one very nice choice is to use the simplest possible material, which is an ideal gas. And that is something where you have molecules that are basically just moving around on their own, and we assume that they're not interacting with the other molecules. So they're just flying around, bouncing off the walls of the container. And as you increase the temperature, as you heat up that system, then those things move faster. And we said that we could base a temperature scale off the pressure reading of an ideal gas in some constant volume container. So just to review then, the pressure is equal to just the force of that gas on some small part of the wall divided by the area of that part that you're looking at. Okay, so the pressure is the force per unit area. And just to get started here, I wanted to have a question to help you just think about that again and make sure you're understanding that concept. So here is a question that relates to this simulation that we had last time. So we talked about how the source of this force that the gas is exerting on the walls is just that you have all sorts of molecules of the gas and they're colliding with the walls. So a huge number of collisions every second. And even though the molecules are very small, there's a lot of them and they're moving very quickly. And so that actually adds up to a significant amount of force, as we demonstrated last time. Okay. So keeping in mind that basic picture, I want you to think about this question. So if I have two different systems, in the second one, I've doubled the height of the box, but I've also doubled the number of molecules. And I want you to understand, think about, is the pressure on the left wall of this container in number two, is that larger? Is it smaller? Is it the same? And as a follow-up to that, I want you to think about, so here we assume the molecules are at the same temperature, that they're moving at the same speed. As a follow-up, I want you to think about, if we double the speed of the molecules, what are the reasons why the pressure on the walls would increase? Okay, so pause your video, think about these questions, and then we'll talk about them. Okay, so the first question is our multiple choice question here. And there are various ways to see that the answer is A, that the pressure should actually be the same. So the first way we can understand that would be, say, using this formula, that pressure is the force on the left wall times the area of the left wall. So we see that the area doubles, but we can also understand that the force on the left wall in number two is going to be twice as much as the force on the left wall in number one. And the reason is that system number two, it's really like taking system number one and then just placing another copy of that on top. And well, if you want, you could remove the wall It won't make any difference. And so the force if you look at the lower half of number 2, there'll be some force on that half. That's the same as the force in number 1. And then on the upper half of number 2, there's also the same force. And so the total force on the left wall in number 2 is going to be double. The total area is double, so the pressure is the same. But maybe an easier way to understand that without going through this calculation is just to think about the microscopic picture. And so if I just zoom in on some part of the wall, a little area of the wall, then the pressure is related to the collisions of molecules with the wall. And in these two situations, what we've ensured is that the density of molecules is the same in both cases. Doubled the volume, but we doubled the number of molecules. And so the number of molecules per volume is the same. Temperature is the same, so they're all moving at the same speed. And so the force per unit area, if I look at a similar small area of box number 1 versus box number 2, you're going to get the same number of collisions per unit time. They're going to be just the same impact, and so you're going to end up with the same pressure. Okay, talking about the extra question, I kind of already alluded to the answer here. So if we imagine, maybe let's look at box number 1 now. If we imagine doubling the velocity of the molecules, then there's going to be two different effects. So first of all, the molecules are going to collide more forcefully with the walls. So the impact of each collision is going to be larger, and so that will end up giving you a larger pressure or a larger force on the wall. So if we imagine a more macroscopic thing, if I'm throwing lots of tennis balls at a wall, and all of a sudden I start throwing each tennis ball with twice the velocity, then we're going to have larger impact on the wall, and so the force from the tennis ball, the average force from these tennis balls on the wall is going to increase. But there's one other effect, which is that as I double the speed of the molecules, they're moving around faster, and so they're actually going to collide with the walls more often. So if I double the speed of the molecules, I'll actually double the number of collisions per unit time. So not only are the collisions harder, the collisions happen more frequently. And so there's these two different effects. If I double the velocity, I get two reasons why the pressure will increase. And actually, in detail, if you think about it, then if I double the velocity, actually the pressure ends up increasing by a factor of 4. Okay. So that's pretty interesting because the temperature, we said, was related to the kinetic energy of the molecules. And that also increases by a factor of 4, half mv squared. If I double v, v squared increases by a factor of 4. So if I double the velocity of the molecules, then the pressure increases by a factor of 4, and the temperature increases by a factor of 4. And so that kind of motivates this definition, or this formula that we had last time, where we said that it's convenient to define a temperature scale using the pressure of an ideal gas in a gas thermometer. So we have this, we have this equation that T, so the Kelvin scale is defined by imagining you have a gas in a constant volume, you're measuring the pressure of that gas, and then you assign a number to temperature by just taking something which is proportional to that pressure. And so to complete the definition of this temperature scale, you're going to need to decide which proportionality constant do you want to use. And so that's equivalent to, like, you want to build this thermometer, you put a pressure gauge on here, and you want to decide how are you going to calibrate the pressure gauge? Which numbers are you going to put next to the various markings? And so it turns out that we just need to choose one particular reference system and decide what we want the temperature of that to be. And then once we do that, then our temperature scale is completely determined. So a very convenient choice, just historically what people settled on for the definition of our reference temperature, is to use what's known as the triple point of water. So we talked about last time how you might calibrate a mercury thermometer by using ice water and marking off 0 degrees at the place where the mercury thermometer level gets to in the ice water. But I also mentioned, and we talked about how we could use boiling water to measure the temp, to calibrate and say that that was 100 degrees. Now, one of the things I mentioned last time was that the temperature of the boiling point of water actually depends on the pressure. And so as you go to less pressure, so if you're very high up in a mountainous area, the temperature of boiling water is actually less than 100 degrees Celsius. Well, if I keep decreasing the pressure, it turns out that the boiling point decreases and decreases and decreases and decreases. And at some point, the boiling point of water actually coincides with this freezing point of water. And so if I had ice water and I decreased the pressure enough, turns out down to about 600 pascals. So that's 0.6% of atmospheric pressure. No, sorry, it's 0.6% of atmospheric pressure. Then your ice water will actually start boiling, and you'll have steam and ice and water all in equilibrium. Okay, so that system exists at only one particular temperature and one particular pressure, to have all of those three in equilibrium. And so that's a system that is convenient to use in order to define our temperature scale. So the Kelvin scale is defined by saying that the temperature of that water at the triple point is 273.16 Kelvin. Okay, and once you have that value, then you can, that basically determines what this constant is for the thermometer that you build. And so then you could use your thermometer to figure out the temperature of any other system by measuring the pressure. And I'm going to give you an example where you'll work that out in just a moment. Okay. And so you'll notice that whereas with the Celsius scale, we ended up using two different systems, freezing water and boiling water, in order to define the scale. With the Kelvin scale, you really only need one reference system. And the reason is that we're using a simpler relation. It's a proportionality relation between temperature and pressure. And so by definition, when the pressure is 0, the temperature is 0. Okay, so that's kind of the other point that we're using to calibrate our scale. Okay. So just to emphasize that in a graph, so we see that in the Kelvin scale, you just have not only is it a straight line, it's a straight line that goes through the origin. So we have pressure is proportional to temperature, and then just this constant will depend on the details of your thermometer. How big is the volume? How much gas is in the thermometer? Okay, so that's the Kelvin scale. Once you define this, the Kelvin scale, actually the modern Celsius scale is defined just by adding on 273.15 degrees. So that's almost the same thing. You just basically shift your axis. And so in the Kelvin scale, the lowest possible temperature is 0. In the Celsius scale, the lowest possible temperature is minus 273.15. Okay. So you might ask, why did we pick this temperature, 273.16 Kelvin, as the temperature of water at the triple point? And basically the reason is that we wanted to choose that to align with the Celsius scale. So if we make this choice, then the difference in temperature between freezing water and boiling water is going to be, at regular pressures, is going to be 100 degrees or 100 Kelvin. And so it's the same temperature difference as in the Celsius scale. So we choose this temperature for the temperature of the triple point of water so that 1 Kelvin temperature change is equal to 1 degree Celsius temperature change. Okay. So the two scales are different. You have this formula that relates them, but the changes in temperature when measured in Kelvin or degrees Celsius are going to be the same. Okay, so now I want you to think about the following question. So let's imagine we've built our ideal gas thermometer. We have placed it in water at the triple point. We measure the pressure, and we find that that pressure is 50 kilopascals. And so now what we want to do is imagine placing the thermometer in some other water. We want to figure out what the temperature is. We notice that the pressure now reads 100 kilopascals. And so we want to know, what is the temperature of the water? So I claim that having done this calibration, we should be able to figure it out. So take a moment to think about that, pause your video, choose one of these answers, and then we'll discuss it. Okay. Okay, so disaster. All right. Slight technical issue with my very high-tech camera, document camera here. Okay, we're back. So let's talk about this question. So what we can do is use our basic idea that in the Kelvin scale, the temperature is proportional to the pressure. So there's really two ways to do this question. One thing you could do is just start with this formula, plug in temperature equals 273.16, and plug in pressure equals 50 kilopascals, and then you'd figure out what the constant C is, and then you could use the formula again to figure out what the temperature is for a pressure of 100 kilopascals. But there's a slightly simpler way to think about it. And so in words, what we can use is the idea of proportionality, that if you double the temperature, you're going to double the pressure. And similarly, if you see a doubled pressure, that means that the temperature is double. And so that's really what's going on in this question. You, in the new situation, have a pressure which is twice as much as the pressure in this original situation where you've calibrated the thermometer. So the pressure reading here is 100, the pressure reading here is 50. And so you can immediately conclude that the Kelvin temperature is double what it was before. And so that's 2 times the triple point temperature, which is 546.32. But this, let me just be a little bit more explicit about this mathematically. So I'll just give you a version of this formula that you could also use that's a little bit more convenient, that just sort of mathematically captures the intuition that I just described. Okay. So I want to say that in these two situations, the equation that we have is going to be true in both cases. So we could say that in the second situation, T2 is equal to this constant times P2. And in the original situation, we had some other temperature, T1, and that's equal to the constant times the original pressure. And so what's a convenient thing to do is to just divide these two equations. So basically the quotient of the left sides equals the quotient of the right sides. And so we could say that T2 over T1 is equal to P2 over P1. Okay, so basically anytime you see a proportionality relation where one thing is proportional to another, then this same logic applies, and it's true that T2 over T1 is equal to P2 over P1, or whatever your quantities are. And so this is sort of mathematically what we're using in the quick way of doing this question. So if we use that as our starting point, then we can say that T2 is equal to this ratio of pressures times the original temperature. And in this case, the ratio is just 2. If I had told you that the new pressure was 150 kilopascals, then it would just be the same, but your ratio of pressures would be 3, and so you'd multiply that triple point temperature by 3. Okay, so let me give you now just one more question. So I'll go back to my slides and show you the question here. So here is a very similar question. And so I want you to think about that question for a moment. Maybe pause the video again and see if you can get this question. Now this one, I'll warn you, there's a little bit of a trick. And in the class, only half of the people got this one right. So be careful and see if you can spot what the trick is and why it's more complicated than the previous question. Okay, so let's do this question. Okay, oh, well, maybe I'll leave that up for you. There we go. Okay, so let's do this question. So what I'm going to do is use the result that I just derived so we're looking to find the new pressure, and we're given that the temperature has increased from 20 degrees Celsius to 120 degrees Celsius. And so what I could use is that P2 over P1 is equal to T2 over T1, but here's the catch. This proportionality relationship is only true if we use the Kelvin scale. So I'll write T2 Kelvin over T1 Kelvin to emphasize that this is only a true equation if we're using our temperatures in Kelvin. And in this question, the temperatures are in degrees Celsius. And so what we have to do is convert those temperatures to Kelvin temperatures by adding 273.15. So we're going to have 393 Kelvin over 293 Kelvin. So P2 over P1 is this, which is approximately 1.3. And so if we have an initial pressure of, 1 kilopascal, then the final pressure is going to be 1.3 kilopascals. Okay. So basically, just be careful when you're doing questions in this course that you're often going to have to convert from the Celsius scale to the Kelvin scale. If your formula that you're using only involves a temperature difference, if it's delta T that comes into it, then you don't have to worry because changes in Celsius temperature are equal to changes in Kelvin temperature. But if you're using a formula like P equals C times T, or a number of the other formulas that we'll see in the course that don't involve a change in temperature, that actually involve the actual temperature, then you're going to have to use the Kelvin scale. Okay. So the Kelvin scale, it's a lot simpler for many types of questions. And so that's why it's sort of a preferred system of units for science and engineering for a lot of situations. All right, where did my slides go? There we go. Okay, sometimes you might even see questions involving the Fahrenheit scale, especially if you spend some time in the United States. And so it's just good to keep in mind these various conversion factors. Okay, so in terms of the definition, we define the Kelvin scale, and then these other scales are really just defined by adding a temperature to the Kelvin. The Fahrenheit scale is simply related to that as well. And you won't need to necessarily memorize these. We'll give them to you if you need them. Okay, so I made this meme, just might be a little bit out of date. Anyways, a while ago, people were using this a lot. This is the most interesting man in the world. And in terms of thermodynamics, he says, I don't always do thermodynamics, but when I do, I use the Kelvin scale. All right, so let me just summarize some things about thermometers. We've sort of understood various ways that you could build a thermometer by using a certain macroscopic property of a system. We said that in order to define a temperature scale, it's convenient to use an ideal gas thermometer. Okay, but it's not always practical to use that ideal gas thermometer to actually make temperature measurements. If you're sick, you don't necessarily want to put a large cylinder of gas into your mouth. And so it's fine to use all of these other different technologies, and you can calibrate these using some ideal gas thermometer. So you could just make sure that they read the same temperature, and then you know that your various thermometers are going to be accurate. Okay, so this one is based on the volume of mercury. This one is based on the temperature dependence of the resistance of some material. Infrared thermometers, they don't even have to be touching the sample. They're just using the property that the infrared radiation coming off of an object changes in its intensity and its wavelengths as you change the temperature. And the other one you might have read about in the textbook uses the thermal expansion properties of solids. Okay, so that's what we're going to get to now. I want to talk a little bit about thermal expansion, and we're going to get into this in more detail next time. So I wanted to show you this picture. This is what happens if you don't properly take into account the thermal expansion properties of your materials. And this is kind of a warning to you. It's a warning in that if you're an engineer and you screw something up, if you forget to take into account some important physical property of your material, and then you go and build something, and something like this happens, then you might have hundreds of years of engineers in the future looking at your mistake in textbooks. Okay, it looks like, I don't know how old this photo is, but I felt like they might have even invented the camera so that they could take a picture of this poor engineer's mistake and then show it to all of the future generations of engineers. So this is a good indication that even though the thermal expansion of solids is a very subtle effect, it's a very small effect usually, it can have enormous important consequences. Okay, so I want to spend a little bit of time talking about the formula that you read about. The basic physics we're going to talk more about next time as to why this happens. But what happens when you have a solid and you increase the temperature, then typically the solid expands. It expands in all dimensions. And right now we're just focusing on the linear expansion. So looking at the length of a brick or a bar of metal that's at some initial length L0 and some initial temperature T. Now we change the temperature a little bit, and what you find is that the change in length is proportional to the change in temperature. So another proportionality relation, as long as the change in temperature is small. Okay, so as long as, and this will generally be true, when we're talking about going from between different regular temperatures on Earth, then typically we're going to end up having relatively small changes in temperature in terms of like, what is the percent change in the Kelvin temperature? And we're going to end up having relatively small changes in length. So the way this formula works is that there's a constant of proportionality. And that constant of proportionality, it depends both on the property of the material, what kind of material it is, and on the original length of your object. So it's kind of easy to understand why this would depend on the original length of your object. Because if you have a brick and you heat it up, it expands a little bit. If you have a brick that's twice as long, that's kind of like having two bricks next to each other. They're each going to expand the same amount. And so the total expansion is going to be twice as much as it would have been. Okay. And so that's why the proportionality constant is just linear in the length. So this expansion is not only proportional to the change in temperature, but if you have the same temperature change, you're going to get twice as much expansion if your object is twice as long. Or another way to say that is that the fractional expansion, if I look at delta L divided by the original length, that thing doesn't depend on the size of the object. So that's actually a very nice way to think about this expansion. It's happening everywhere in the object. There's a certain fraction by which the material expands. And so then if I have an object that's twice as big, then the actual linear amount of expansion is going to be twice as much. Okay. Now, once I take into account that factor of L0 here in the formula, the remaining proportionality constant, that only depends on which material that I'm talking about. Okay, so the coefficient alpha, it really is just a property of like copper or brick or steel or whatever it is that you're interested in. Okay. One thing to mention is that, even that, like I said, most physical properties of objects can change with temperature. So even that proportionality constant changes with temperature. But it's mostly at typical temperatures. If you have something like copper, it's going to be pretty much constant over the range of temperatures that we normally work with. But if you're being very careful, if you're in a very high temperature situation, you might want to be careful to look up the correct coefficient alpha for the temperature that you're using. Okay, so just to give you a chance to process that formula, to get an estimate of how big is the actual expansion in a real world situation, I want to talk about this question here, have you think about that. So this is the Verrazano Narrow Bridge. I think it used to be the longest single span bridge in the world. The question we're going to ask is, how much longer will the bridge be during the summer compared with during the winter? And this bridge is in New York, so that's a city with relatively warm summers, snow in the winter, freezing temperatures. And so using that information and the information that the bridge is about 1 kilometer long, and that for the materials of the bridge, we're going to assume that alpha is about 10 to the minus 5 inverse Kelvin, then think about how much is this bridge going to expand. Okay, so pause your video, do the calculation, and then we'll come back and do that when I get set up here. Okay, so let's work through this. So this is mostly just plugging things into the formula. So I'll write down the formula that we have to start with. So one of the interesting things about this question is I didn't really tell you specifically what these temperatures should be or what the temperature change should be. And this is going to happen sometimes in questions where we just ask you to estimate the size of an effect. We won't necessarily tell you exactly what the temperatures to use are. So you just have to, notice the answers to this question, 5 millimeters, 5 centimeters, 50 centimeters, 5 meters, they're all differing by at least a factor of 10. And so in terms of estimating what should we use for delta T, well, we want to just make sure we're accurate within a factor of 10. So we just have to think, well, how hot are places typically in the summer? And how hot are they in the winter? And then just get a reasonable estimate. As an engineer, you don't know exactly how hot it's going to be next summer in New York, but you can estimate what the highest temperature that it's likely going to be. You could estimate what is the lowest temperature it's likely to be. Of course, you could look up in tables in historical weather records what the record temperatures are. But for this purpose, you can at least get an estimate, and that's what we want to know. We just want to know roughly how much is this bridge going to expand. And so if I think about it in terms of a summer temperature, New York City probably gets up to 30 degrees frequently, probably hardly ever gets up to 40 degrees. So let's take 30 degrees as our temperature. Winter, I mentioned that it's cold, it's snowy, so definitely below 0. Let's imagine that New York might get down to minus 20 degrees Celsius in a typical winter. Okay, and so that means that delta T is 50 degrees Celsius, or equivalently 50 Kelvin. Okay, so once we have that, we can plug that into here. Our L0, we can use 1 kilometer. Well, it's really 1.3 kilometers. The 0.3 is not going to matter. The alpha is 10 to the minus 5 inverse Kelvin. And so we just multiply all those together. Delta L equals 10 to the minus 5 times 10 to the 3 times 50. And so that's 50 times 10 to the minus 2 meters. Okay, so we're using SI units for everything, and so the final answer is going to be in meters. And 10 to the minus 2 meters is a centimeter, and so our answer is 50 centimeters. Okay, and so again, you know, I was just trying to get the right order of magnitude here, and so I didn't care that it was 1300. It was okay for me to just use 1000, and it was okay for me to just estimate that delta T is on the order of 50 Kelvin. Okay, so that's, you know, coming back, that's quite a bit of expansion. That's half a meter of expansion. And so if you construct that bridge and you don't take that into account, you could definitely have problems. And so what people end up doing is building in places in the bridge where there's room for the segments of the bridge to expand. And so you see in the picture, this is a bit of a spacer. And so if this part of the road, if that segment expanded, sorry, coming back, see me, hello. If that segment expanded, then there's a little bit of space for those teeth to come together. And so you just want to make sure to have enough of those spacers so that your bridge will be fine in the summer, it'll be fine in the winter, and you won't have any embarrassing situations like this one. Okay, so that's all for today. Next time we're going to talk more about thermal expansion. We're going to talk in more detail about why things expand when you heat them up, and we'll talk about more applications.